not integrable. It's just the explicitly taken value of the square of phi at x equal to 0, because it's produced, formally it's also an integral term, but it's this integral includes delta of x, therefore the integration is performed trivially, and we just obtain this extra term produced by the internal delta function of potential, just as in this purely local form, without any integration. Now, according to the general principles of the variation approximation, we should adopt what is called the ansatz, the trial wave function, and the simplest possibility is written here. So we can take the combination of cosines and sines. Of course, we should select the arguments. For example, here is pi, here is the coefficient is pi, here 3 pi, here 2 pi, but this is the argument of sine rather than of cosine, because automatically each term must satisfy these boundary conditions at the edges of the potential box. So that each term in the wave function must vanish if we want to be sure that the entire wave function vanishes. Then we, A, B, and C are arbitrary coefficients, which we should find from the variation approximation. And now the meaning of all this approximation is the first two terms obviously represent even functions. So they are going to somehow approximate the symmetric wave function. But the third term, it also satisfies the boundary conditions, but it is anti-symmetric. And if we will have a solution in which B, the amplitude in front of this term, is different from 0, the entire wave function will become asymmetric. It implies that we have what is called semi-symmetry breaking, the appearance of such non-trivial asymmetric solutions. And by the way, what should be also mentioned is the fact that obviously this ansatz does not agree with this internal boundary condition, because internal boundary condition implies that we should have a jump of the first derivative at point x equal to 0. However, obviously the ansatz does not have any jump. All terms are not only these terms themselves, but also their first derivatives as functions of x, they all are continuous at x equal to 0, which simply means that the ansatz is not very accurate. It actually does not take into regard the presence of the jump, but nevertheless, it makes sense to try to analyze this ansatz and see what it will predict, because what we should really try to predict, even if we cannot exactly take into regard the presence of the jump, is the transition from symmetric to asymmetric solutions. And as we will see, although this ansatz is not very accurate, it makes it possible to predict this phenomenon. So what we do technically, we substitute the ansatz into the Lagrangian. We simply sub framework of the variation approximation as an explicit simple polynomial function of three parameters A, B, and C. And then we write the standard system of the variational, or in other words, Euler-Lagrange equations. We demand that for the approximate stationary solution, the first derivatives of the Lagrangian with respect to all the three parameters must be simultaneously equal to 0. So this will give us, but also I mentioned that there is another analytical approximation, much simpler one. We can just explicitly develop the asymptotic analysis of this equation, assuming that epsilon is a very large parameter. So after some technical details, which I will not present here, because they are rather boring, it will take too much time, this limit case of very large epsilon produces the approximate results. In particular, how we can represent these results. In particular, we will see that in this limit of very large epsilon, what it means physically. Very large epsilon means that this potential barrier is very tall. Its approximation predicts that the ground state, first of all, of course, we would like to find the ground state, which provides the minimum energy. So it will predict the ground state with this particular value of the total norm. The norm is defined here. It's an obvious definition of the norm. For larger values of n, it's shown by this dotted line, but it becomes now unstable. It is destabilized by this, what is called the symmetry breaking bifurcation. Simultaneously, we obtain a new solution. The new solution is characterized by the non-zero value of theta. Actually, strictly speaking, of course, we obtain two new solutions because we can have the solution with theta and then the solution with minus theta, which means to zero. But it makes sense to show only one curve because the other will be just its mirror image. We would not show anything new. Now, the continuous curve shows the result of the full numerical solution of this problem, and not only this numerical solution for the shape of this wave function as a ground state, but also the fact that it is shown by the continuous curve implies that it is stable. It can be also checked numerically that it is stable against small perturbations. Now, the dashed line simultaneously shows the prediction of this variational approximation. So just taking these Euler-Lagrange equations, we can solve them numerically. We can then calculate this way. We can reproduce the approximate wave function, which is predicted by the variational approximation, calculate its norm, and eventually produce for the variational approximation the value of theta as it is predicted by this approximation. And we see that the analytical approximation for the asymmetry is practically identical to the complete numerical solution. So in this sense, this simple variational approximation is quite accurate. And even if, as I stressed, the variational ansatz ignores the presence of the jump of the first derivative at x equal to 0, in spite of this inaccuracy, the prediction of this bifurcation diagram provided by the variational approximation is quite accurate. Next, we can actually, I guess this was the last plot, which was shown at the last minute of the week ago. It makes sense to discuss it again. We can present the results in a different form because, excuse me, if we vary the value of n, it's a norm, the total norm of the wave function, obviously, we will accordingly vary, due to the nonlinearity, the eigenvalue of the ground state, or the chemical potential mu, will depend on n. And so here, the solutions of the same problem are shown in terms of the dependence between n and mu. So to compare it with the previous plot, here also n is varying, and of course along this curve we will have the values of the chemical potential. Simply the chemical potential is not shown in this plot, but it is shown here. Okay, so what we can see, the continuous curve shows the ground state of the system as found from the numerical solution. And again, here from so here we can see something quite similar to what we saw in the previous plot. In the previous plot, we see that when n took values between 0 and roughly speaking 5, we had the symmetric ground state. Here we see the same. When n takes values on this axis between 0 and 5, we have this segment, which actually implies that it is a stable. By definition, it shows the stable, symmetric ground state, and it still remains stable. Now, this is a critical point at n equal to 5, the same critical point that we saw here, the same one, where we have the onset of the spontaneous symmetry breaking. So here, from across this point, we can continue by this dotted line. We can continue the numerically found symmetric state, but it is now unstable, not so interesting. And we have a new solution, which is represented by the continuous line, which exactly corresponds to the new asymmetric stable ground state obtained from the numerical solution. Now, simultaneously, these two dashed curves, they show the prediction of the variation approximation. So first of all, this top dashed curve, it shows the prediction of the variation approximation for this unstable symmetric solution beyond the symmetry breaking point. So we see that here the prediction is quite accurate, although it's not very interesting simply because it predicts accurately, but it predicts the unstable solution. Now this bottom dashed curve shows what is predicted by the variation approximation for the asymmetric stable ground state. Now we see that this prediction is less accurate. There is some discrepancy between the numerically found ground state and the variationally predicted one, but still overall the prediction is maybe called reasonable, taking into regard that it is actually it was based on a rather primitive ansatz. Principle that can be improved if more terms are included, but of course then technically all the analysis will be much more cumbersome and maybe it is not worthy the effort. Okay, now this is to further illustrate the variational approximation and the full numerical solutions. These are particular examples of the bound states which are both produced as numerical solutions and are predicted by the variational approximation. So this here we take a particular values of the parameters. Epsilon, the strength of the potential barrier is 3, and the total norm is 10. According to this plot also was produced for epsilon equal to 3. So we see here that if n is equal to 10, we conclude that the symmetric wave function is definitely unstable, and what is stable is sufficiently strongly asymmetric one. Now we can see examples of that. For these values of the parameters, these are unstable symmetric bound state. So again, the continuous curve shows the result of the numerical solution, and the dashed line shows, dashed curve shows the variational approximation. So here, actually, we should mention that we definitely have, as concerns the numerical solution, we definitely observe a local minimum at x equal to 0, which is very natural because we have the presence of the repulsive potential barrier here. But strictly speaking, we don't see here any jump as derivative. The first derivative remains continuous. The point why it remains continuous, because if we want to obtain the numerical solution, is that for the numerical solution, we cannot use the ideal delta function. So what was used to produce the numerical solution it was not the ideal delta function, it was some standard approximation for the delta function in terms of some narrow, usually it's a Gaussian approximation, some Gaussian function with a sufficiently small width and large amplitude, and it satisfies the normalization condition, which actually is exactly the same as for the delta function. But in that case, of course, when we use this approximation for the delta function, there is no reason to expect that we really have the jump of the first derivative. Everything remains continuous and smooth. Okay, and now what is more interesting actually is to look at this right panel, because this panel shows the stable asymmetric ground state, which we have in this case for these parameters. And once again, we see the continuous curve and we see the dashed curve. The continuous curve shows the numerical solution. The dashed curve shows the variation approximation. We see that, of course, there is some discrepancy, but it's not large. And it implies that this quite simple variation approximation makes sense. It predicts something which is relatively close to the numerically exact results. So it is usable. Okay, now another illustration of what happens here, dynamical illustration. So once again, if we have exactly the same case as shown here, and as I said, we definitely expect that this, now we are talking only about this numerical solution. This numerical solution is definitely unstable. And now this particular simulation illustrates how this instability develops. So the input is shown by this bold black curve. It is exactly the numerically found unstable symmetric bound state. And then we run the simulation of the full time-dependent nonlinear Schrodinger equation, and it demonstrates this result, namely, due to, actually here no explicit perturbations are introduced. The perturbations are introduced simply by small truncation errors of the numerical scheme. And this intrinsic, very small this very weak numerical noise is sufficient to initiate the development of the instability of this input. And we see that the instability actually indeed tends to transform the symmetric input into a strongly asymmetric solution. So we see that it spontaneously makes the value of the wave function or density, it's the absolute value of the wave function, the absolute value of the wave function in one section of this, in this case it's left, in the left section of the box. Spontaneously the amplitude becomes much larger, in the other it becomes much smaller. So this is exactly the dynamical realization of the spontaneous symmetry breaking. Of course, this dynamical evolution will not produce exactly the stationary state, because this is, by definition, what we obtain here is not a stationary solution. We obtain some solution with some internal dynamics, with some internal oscillations, but still its overall shape, although it's not, at this later stage of the evolution, it's not very clearly seen as a figure. Nevertheless, it's easy to understand that it's quite, overall, it's quite similar to this strongly asymmetric configuration. Okay, now we can summarize these results. Now we can ask the following question. Okay, let us take different values of our control parameter is epsilon. Epsilon is the strength of the central potential barrier. Maybe let us look once again at the original equation. So the original equation is here. So this is because we normalize the size of the potential box to be 1. Epsilon is a single control parameter in this model. And now we can ask the question, okay, if we have effects such as spontaneous symmetry breaking, for example, here, for epsilon equal to 3, we see that the spontaneous symmetry breaking sets in at the particular critical value, bifurcation value of n, which is close to 5. And then to characterize the entire system, it will be natural to collect the numerical data and predict what will be the critical value of n of this point of the spontaneous symmetry breaking as a function of epsilon. So this results, which provides a summary of all the entire analysis, they are shown in this plot. So this is this bifurcation value of n, or critical value, at the point of the symmetry breaking, versus as a function of the control parameter epsilon. And so it starts actually not exactly okay, yes. And then actually values of n start from 0, but values of epsilon, it's not explicitly, the first value of epsilon is not explicitly written, but you can see that actually you can see that at this point, the value of the bifurcation parameter is still finite, it's not infinitely large, which means that this first value of epsilon is not 0, because if epsilon is equal to 0, we should not have, of course, any spontaneous symmetry breaking, which formally means that the critical value of n will become infinite. But here, actually, this plot is confined to this interval, because when epsilon is very close to 0, the critical value of n becomes very large. It may be difficult to extend this plot so that the value of n will be very accurate. Okay, so this is the overall characteristic of the system. Now, this is a numerically found dependence between n and epsilon, and this dashed curve, once again, shows the prediction provided by the variation approximation. So we see that, of course, they intersect only at one point, somewhere here at epsilon close to 2 maybe. Otherwise, there is some discrepancy. Sometimes the variation approximation predicts the critical value, which is larger than the numerical value, sometimes smaller, but overall it gives a correct qualitative picture, the variation approximation. Now we see that the accuracy of the variation approximation deteriorates for large values of epsilon, and it's not difficult to understand why, because others was too simple. In particular, it ignored as I mentioned already, the jump of the first derivative, or something which is similar to the jump at x equal to 0, but when epsilon is very, very large, this feature, this jump or quasi-jump, becomes actually very salient, very strong feature, and therefore the answers becomes quite inaccurate. Therefore, for very large values of epsilon, the variation approximation becomes inaccurate. However, we have another analytical approximation, which I mentioned, for large values of epsilon. So we see that when epsilon is not very large, this approximation is quite inaccurate, but as we increase epsilon, gradually we see that this large epsilon approximation becomes closer to the numerical approximation, and therefore it becomes usable for really very large values of epsilon. Okay, now there is another interesting thing that we can consider in the framework of exactly the same model, because thus far we were talking only about the ground state. So the ground state is a solution with the lowest energy, and in the case of the linear equation, or in the case of weak nonlinearity, it is represented by the symmetric wave function, and later it undergoes the symmetry breaking. Later, I mean, for the stronger nonlinearity. However, as we know from quantum mechanics, the infinitely deep potential box has actually an infinite spectrum of bound states. And then it may be interesting also to consider what happens to the first excited state above the ground state. So it will be, according to the general principle of quantum mechanics, in the linear limit, it will be automatically an anti-symmetric wave function. And now the question is, what will happen in our model with the first excited state? Actually, if we have the model with the ideal delta function, we can immediately understand that the stationary solution for all anti-symmetric bound states, including the first excited states, are simply exactly the same as they were in the linear limit. Why it's obvious? Because let us look again at our model with ideal delta function. This is a stationary equation. What we see, if we want to find the solution with the anti-symmetric phi, of course, the anti-symmetric or odd function automatically vanishes at x equal to 0. but the entire barrier is placed also at x equal to 0, which means simply that for any antisymmetric bound state, this entire term vanishes, becomes equal to 0, and therefore we will have actually the same situation which we have in the absence of any potential barrier. Well, I said actually that the same as in the case of the linear Schrodinger equation. Of course, it's not correct because we still have the nonlinear term, but I mean in the case when we want to find any bound state which is antisymmetric, it will be exactly the same as its counterpart in this potential box without any splitting potential. So in that sense, we can say that the presence of the splitting potential provides no effect. However, what is also important is not only to obtain the stationary shape of this antisymmetric excited state, but it's also important to explore its stability. And for the stability, the presence of the potential becomes essential because we may have, in particular, small perturbations which do not vanish at x equal to 0. There is no reason to assume that small perturbations must also vanish at x equal to 0. Therefore, the result of the analysis will be definitely of the stability analysis will be sensitive to the presence of this delta functional barrier, and therefore what will happen eventually, the result of the actually this is only the numerical investigation without an analytical approximation. If we keep increasing the value of n of the norm, in other words, we increase the effective strength of the nonlinearity, what happens to the antisymmetric states is shown by this plot. The plot shows the dependence between the chemical potential, in other words, the eigenvalue of the energy for this first excited state, and the total norm. So first of all, we see that, of course, this eigenvalue is always higher than the eigenvalue for the ground state, because it's the excited state. And then we see that up to some finite, when n varies, actually here it's static somewhere from here, because here we have this line starts from some finite value of n, not from n equal to 0, but if we take smaller values of n, we will have just the extension of this curve, which is not very interesting. And the continuous form, the fact that it's shown by the continuous curve implies that up to this critical point, this is a family of stable solutions. So up to this point where the nonlinearity becomes strong enough, the antisymmetric excited states are stable. Now, something non-trivial happens at this value of n, namely, the antisymmetric state becomes unstable against small perturbations. And therefore, still, the family of these antisymmetric solutions can be extended. It is extended by the dotted line, but it is now completely unstable. And simultaneously, for comparison, the same results which were already discussed for the ground states are also included. So for the ground states, the symmetry breaking point is here, and as we discussed it already, then the symmetric ground state will be formally extended, but as an unstable solution. And then we have here the appearance of the new asymmetric stable ground state, which is a true ground state of the system beyond the symmetry breaking point. Particular here we have some, so here we have up to this point, we have in terms of the total full set of these two solutions, we have the bistability. Both solutions for these values of the chemical potential, they may coexist. Or in other words, there is some interval of the norm between this, actually below this point, where there is bistability in terms of the norms. For the same norm, we may have both the ground state is stable against small perturbations, and the first excited state is stable. Now, at this point, where the antisymmetric state becomes unstable, there is no bifurcation in the sense. Here we saw that the unstable symmetric state was replaced by the newly appearing stable asymmetric one. here we have simply the loss of stability of the antisymmetric state, but no additional, at least no visible additional stable solution appears, which would replace the unstable antisymmetric grounds, the first excited state. So this is
Boris.
Yes.
Boris.
Yes.
Please, I would like to know how you measure the stability in terms of the splitting barrier.
The stability was determined from the numerical solution. Actually, it was identified, as it's usually done, by means of two different methods. First, it's possible, so to say, more systematic and more accurate method. We can take this full time-dependent equation from which we started the model. The equation is written not here, but previously here, right? We can then write the system of linearized equations for the small perturbations. In the studies of Bose-Einstein condensates, usually the system of linearized equations is called the system of Bogolyubov-Dschang equations. And then if we have the numerically exact stationary solution, it is possible to solve numerically the linearized equations for the small perturbations and identify eigenvalues of small perturbations. And eigenvalues, they determine if we have the instability or not. So if there is a instability growth rate as an eigenvalue of that linear system with a non-zero real part, it means that we have the instability. If all eigenvalues for the linearized equations are completely imaginary, it means we have neutral stability. And then another approach, which is was already illustrated actually by one plot here. It's illustrated by this plot. More straightforward approach is, once we can find from the numerical solution of the stationary equation, we can obtain the solution. We can just try to use it as the input for the time-dependent equation, run direct simulations, and see what will happen. So if it is stable, it will simply keep its shape. If it is unstable, we will see something like what we observe here. It will spontaneously start to change, and the system will definitely demonstrate its trend to replace this unstable solution by some new solution. Particularly in this case, the system wants to replace the unstable symmetric state by the stable asymmetric one. Okay, so this is how the stability was identified.
So the stability is according to the shape of the wave function?
Well, of course, first we find stationary solutions we take with particular shape. When we find them as stationary solutions, we don't know if they are stable or not. And then we, in the simplest case, what we do, we run direct simulations using these shapes as initial conditions, and we try to see if the direct simulation will demonstrate that the system keeps this input, or it starts to destroy it, which implies that they're unstable.
Okay. Nathan is also asking a question about.
Yes.
Nathan is asking a question through charge.
What question?
He's asking about the. Let me see if I can have. Nathan, can you ask your question aloud?
So, my question is that what will happen if we had a double barrier of potential?
If we have what potential?
If we had a double barrier of potential.
A double barrier. You ask double barrier. Once again, what barrier? Double barrier?
Double barrier of potential. Because
double
the result
barrier.
Yes, double barrier.
Okay, so I'm not sure that I understood
Double
this
barrier as double well.
Double well,
Yes.
double well, okay.
Double well, yes.
Okay.
Yes.
Okay. If we have the double well, the situation will be situation will be different. Actually, we will, you know what, it makes sense to discuss this issue a little bit later, because this is another topic which will be included hopefully still today. And therefore, it will be much easier to discuss it, because later we will have a direct illustration of exactly this case with a double barrier. Double potential well. So we will have a chance to discuss it directly. Let us postpone this, okay?
Okay, sir.
Because it will be explicitly included. Excuse me. Okay, and finally, yes, the last illustration of this particular model is the summary of the results. This time, so we already discussed the summary of the results for the stability and instability of the ground state, but now we also may produce a similar picture which summarizes the results of the analysis of the stability for the first excited state, the antisymmetric state. The picture is very simple. This is a curve in the plane of the control parameter epsilon. It is strength, or as I said many times, strength of the central splitting potential barrier and the total norm. And so what we should what we should expect from this plot is for some particular value of epsilon. Here epsilon is fixed to be 3. When the norm becomes too large, in other words, once again, the nonlinearity becomes too strong, the first excited state will become unstable. So we should expect the transition from stability to instability with the increase of n at fixed epsilon, and this is exactly what we can see from this diagram. We can fix any value of epsilon, there is some respective critical point. When norm takes values below this critical point, the first excited antisymmetric state is stable. Above this critical value, it becomes unstable. So particularly, if we take epsilon equal to 3, we will have the particular value of norm, which corresponds, roughly speaking, something like between 15 and 20, is the same critical point which we can see in this example. Okay, now let us proceed to a new, another particular model, which also is an important example of the spontaneous symmetry breaking. This is let me remind that the general title of this large topic that which is a subject now is spontaneous symmetry breaking in the dual core systems. So the previous model, in a sense, was also dual core in the sense that this potential barrier splits the it splits the potential box into two boxes which are separated by the barrier. But now we can see another model which literally demonstrates the structure built of two cores. Okay, so this is something which is a very important. It finds very important realizations in optics. In optics, in many cases, people are dealing with so-called couplers, and the couplers. This means in fiber optics we have two parallel optical fibers, this one, and they're separated by some dielectric barrier. However, photons can actually can jump across. So there is actually real industry which produces all kinds of couplers in optics, but it should be also mentioned that now we are going to discuss the dynamics of a coupler in the nonlinear situation, while in practical applications in optics, the couplers usually operate in the linear regime. Okay, so now, first of all, the system of the equations for this case. So as we discussed it more than once, the propagation of light in the optical fiber in the simplest case is governed by the nonlinear Schrödinger equation. Of course, under the condition if the group velocity dispersion in the fiber is anomalous. But this is a practically important case because in standard optical fibers, the dispersion is indeed anomalous. Therefore, actually, fibers may support solitons. So if we take a single fiber, then the amplitude of the electromagnetic field in it is called U, and we have this familiar nonlinear Schrodinger equation. Z is the propagation distance along the fiber. Tau, this is the so-called local time. Formally speaking, it plays the role of the coordinate, but physically, it's a combination, linear combination of the physical time and the propagation distance. Therefore, solitons, which can be supported by this system, by this equation, they are called in optics temporal solitons because their structure is observed as a structure with respect to this temporal coordinate tau. Now, this is the usual cubic self-focusing term, the curve nonlinearity. Now we have the second equation for the second waveguide, which is just essentially the same equation with another amplitude V instead of U. And now we have here the coupling terms. The coupling terms are linear with some effective coupling coefficient capital K. It's a constant. Maybe positive or negative, doesn't matter. Why it doesn't matter? If it is negative, we can just rewrite this system instead of V. We can introduce the other variable minus V. And then in terms of U and minus V, K will become, instead of being negative, K will become positive. Therefore, we can assume that K is always positive. And this is the simplest possibility, which is practically important when we assume that the effect of tunneling is linear. And so this means, in particular, in the first equation, that we have the term with which is linear with respect to V. V is the amplitude of the electromagnetic field from the second core. So some fragment of the amplitude of the electromagnetic field from the second core can actually tunnel into the first core, and therefore it appears in terms of this linear term in the first core. And vice versa, we have the term which is linear with respect to the first amplitude in the second equation, in the parallel core. So this is a system of two coupled nonlinear Schrodinger equations. Now, this model becomes quite popular, and theoretically, long ago, many people actually studied what happens to solitons in this dual core system. And what happens, as we will have a chance to discuss, is the fact that, of course, we can obviously have symmetric solitons when U and V are simply equal to each other, and we will have anti-symmetric solitons when V is minus U. But then, due to the presence of the nonlinearity in each core, a non-trivial fact is that we may have the spontaneous effect of the symmetry breaking, and depending on the energy of this soliton, so again, effectively, depending on the strength of the nonlinearity, when the nonlinearity is strong enough, we will observe that the symmetric, natural, so to say, obvious symmetric soliton will become unstable. It will be destabilized by the symmetry breaking effect, and as a stable solution, it will be replaced by a new soliton, which non-trivial one, which will be asymmetric. Asymmetric, it will mean that it will have different amplitudes in the components U and V. So we will have a chance to see this today still. We have enough time for that. And then, so theoretically, this spontaneous symmetry breaking of solitons in the dual core fibers was studied long ago, as a matter of fact, so even more than 30 years ago, in a number of works. But experimentally, it was not observed at that time. It's not because the experiment is very difficult. Somehow experimentalists were not very much interested in this, and the direct experimental observation of the spontaneous symmetry breaking of the optical soliton in the dual core fiber was reported only relatively recently in this particular work. Okay, now let us proceed first of all to the analytical approximation. So if we want to, first of all, to try to predict some analytical results, we cannot produce an exact analytical solution for the asymmetric soliton. This is our objective. Of course, for the symmetric soliton, these equations will be simply equivalent to the traditional classical nonlinear Schrodinger equations, so we know all the soliton solutions, but it's obvious. What is not obvious is how if the asymmetric soliton with unequal amplitudes may exist, how to construct it. There is no possibility to do it exactly, but we can once again apply the variational approximation. First of all, this is the ansatz. So we take two components, u and v. So we want to look for the stationary solutions. Therefore, we assume that the dependence on z is actually factorized in terms of this obvious phase factor. So we p, this is what is called the propagation constant or wave number. Then a is the common amplitude of this soliton, and then we introduce this parameter theta. Parameter theta obviously determines the possible asymmetry. If theta is equal to pi over 4, obviously both components will be equal to each other. But for values of theta different from pi over 4, we will have the difference in their amplitudes, so we will have an asymmetric soliton if it may exist. And of course, because it's a soliton, it must be also a function of the temporal coordinate tau. So here, the simplest possibility is to assume that this temporal shape is exactly the same as in the classical solitons for the single nonlinear Schrödinger equation, represented by hyperbolic secant, and W is another variational parameter which determines the width. What is essential, actually, is a comparison with the numerical solutions demonstrates when we have the linear coupling between the two equations, the amplitudes of this asymmetric soliton may be quite different, but the temporal width with respect to coordinate tau is essentially the same. Why it's essentially the same? Because this is as a matter of fact dictated by the linear coupling. Because roughly speaking, if we have the particular width of the u component through this term, it will also impose essentially the same width onto the v component due to the linear mixing between them. Okay, therefore this is the ansatz when we have different amplitudes of the two components but identical widths. And then we have this, one can produce some predictions. So first of all, one can define the total energy of this soliton. This is exactly the same which was already mentioned today, but under the name of norm in another context. So this is essentially the quadratic norm. In terms of, for temporal solitons and fiber optics, it's essentially the energy of this light signal. And in terms of the ansatz, it takes a simple expression in terms of the amplitude and W. So the asymmetry parameter is introduced in such a way that the total energy does not depend on it. But then we can explicitly introduce the asymmetry parameter. So today it was already introduced in a different context. Maybe we can for a moment jump back to recollect it. So this was a definition of the asymmetry parameter. Now we have essentially the same definition. So what we do, we separately calculate the energy of each component of this soliton, and then the asymmetry is defined exactly as before. The difference between the two energies divided for the sake of rescaling by the total energy. So in terms of the ansatz, it will be easy to see. It will be cosine of 2 theta. So once again, if theta equal to pi over 4, cosine of pi over 2 is 0. So for the symmetric soliton, we have 0 value of the symmetry parameter. But for other values, yes. Is a question? No. Okay.
No.
Okay. So for theta equal to pi over 4, formally speaking, we have indeed 0 as it should be. And for different values of theta, we have non-zero value of this asymmetry parameter. Okay. And now we can proceed with this machinery of the variational approximation, calculate the Lagrangian, write the Euler-Lagrange equations for the parameters. We can skip this technical part because it's actually will be rather boring and will take long time, and we can just demonstrate the result. The result is shown once again by means of the diagram, which illustrates the spontaneous symmetry breaking. Now, what we show here. So this is what is shown here is actually completely the prediction of the variation approximation. At this moment, the numerical results are not shown, only the prediction of the variation approximation. And what we see in this prediction. So this is, as a control parameter, we have the total energy. So once again, as energy increases, obviously the nonlinearity becomes stronger, and then we should expect that some non-trivial phenomenon may happen when the energy will become sufficiently large. For convenience, the energy is scaled by dividing it by the natural scale of energy, square root of this coupling constant K in the system of coupled equations. As a matter of fact, it's possible to apply the additional scaling and simply say that K is equal to 1. Okay, so this is the energy, and this is cosine of 2 theta. So just a minute ago I said cosine of 2 theta is a measure of the asymmetry. Now, for the values of energy between 0 and this critical value, we have the continuous line of the asymmetry equal to 0. So here we have obvious symmetric solutions, obvious symmetric solitons, and they are completely stable. Now, at this critical point, the spontaneous symmetry breaking bifurcation happens. First of all, what it does, it destabilizes the symmetric solitons. Of course, the symmetric solution does not disappear. It actually extends beyond this point, but it extends, as is shown by the dashed line, as an unstable solution. Now, also similar to what we discussed already in the previous model, at this point simultaneously, a new asymmetric solution appears. Also, it was mentioned already today that if we want to plot the full diagram, we should plot actually both positive and negative values of the asymmetry parameter. Simply one is the mirror image of the other. So in principle, it's enough to look only at the, for example, top half of this diagram, but maybe it's actually more convenient to see simultaneously the same diagram for the mirror image state. Okay, and then what is different from the previous picture that we discussed today? Previously, we had a similar diagram of the spontaneous symmetry breaking. However, as we can see it as a matter of fact, here, yes. In this simple picture, what we saw that this is what is called the forward bifurcation diagram, or sometimes supercritical. And this means that after this point, we have the new branch of the asymmetric solution, and as we keep increasing n, this branch goes forward. Therefore, it's called the forward bifurcation, or also it's called the supercritical bifurcation. Supercritical because the non-trivial solution appears at values of n which exceed the critical value. So the non-trivial solution, asymmetric one, exists in the supercritical region. Now here, for the current model of the dual core optical fiber, the character of the bifurcation is really different. So it is, of course, again, the symmetry breaking bifurcation, but it's a different type of the symmetry breaking. Namely, what we see immediately at this point, we have the appearance of this asymmetric branch, but it does not go, originally it does not go forward. Originally, it prefers to go backward. It means that actually we may have in some narrow region of the energy, we may have, when still the symmetric solution is stable, the asymmetric solution already exists, which means that we have some narrow subcritical region. Subcritical means that the energy is smaller than this particular critical value, at which we already may have an asymmetric, non-trivial asymmetric solution. For this reason, this bifurcation diagram is called subcritical. The entire setting is called subcritical, and also there is another name. The same bifurcation diagram sometimes is called the backward bifurcation for an obvious reason, because this time the new branch of asymmetric solutions first goes not forward but backward. And then it can be found and demonstrated, in particular by means of the rational approximation, but also numerically, it can be verified that as long as the branch of the asymmetric solutions is going backward, it is unstable. Therefore, you can see that this segment is shown by the dashed line. However, this region of the where we have the subcritical solutions is quite narrow. So then, if we follow the evolution of this family, it actually reaches this particular turning point. At the turning point, it actually turns in the forward direction. here, and then simultaneously it becomes stable. So this is a point of the turning point provides for the stabilization of the asymmetric solution. And the variation approximation predicts particular values of the, first of all, it predicts a particular value of this point. It's called asymmetric, of this particular value of the energy, when for the first time the asymmetric solutions appear subcritically. And also it predicts this critical value of E, slightly larger value. So you can see that here the factor is 5.51, here 5.33. So indeed, okay, I'm sorry. Actually, what it should be said exactly in the opposite way. For the first time, the subcritical solution appears. It appears at this point where the energy is slightly smaller than the critical value, at the point where we have the destabilization of the symmetric solution. So this, we can say that in this narrow interval of the energies, we have the effect which is called bistability. In this region, we simultaneously have two different stable solutions. The symmetric solution is still stable, but we already have the new asymmetric solution, which is also stable. Strictly speaking, it may be also even called not bistability, but tristability. Why tristability? Because together with this asymmetric solution, we have its mirror image here. So it means that if we have spontaneously larger energy in one core than in the other, we of course will also have another solution when exactly in the opposite core, we have the larger energy. So which particular core will be chosen by the system to have a larger energy in it? It's simply accidentally chosen by the initial perturbation. Okay, so what concerns technical aspects of this analysis, what should be mentioned that this is a prediction of the variation approximation for this critical value of the point. This is a critical value of the point. Okay, so let me again say it in a consistent form. Okay, this is the point. Actually, this value of energy corresponds to this point where, for the first time, we have the creation of the subcritical asymmetric states. Next, we have this critical value of the energy. The critical value of the energy is also predicted by the variation approximation and given by this value. Now, what we can do, we can compare, first of all, these two values. As we see that indeed this value, it's actually written for the square of the energy. This value for the square of the energy, 6, is slightly larger than this value at that point. So it means that indeed, as shown in this diagram, the destabilization of the symmetric state happens later at a slightly larger energy than we have the chance to create the asymmetric subcritical solution. Now, what also is interesting, this point of this critical value of the energy, where I have the destabilization of the stable state, can be found in the exact analytical form without any approximation. Why it's possible? It's possible because how can we predict the destabilization? We should take the exact symmetric solution. The exact symmetric solution, of course, is available as the exact one because it's simply the classical nonlinear Schrödinger soliton. Then we should write if we want to accurately study the stability problem, we should write the linearized equations for small perturbations around this exact stationary solutions. And then, carefully looking at these linearized equations, one may have a possibility to find the exact solution of this linearized system, which signalizes the onset of the instability. So this is a specific exact solution at which the instability growth rate is exactly equal to 0, which means that this is the critical point at which instability is going to emerge, to appear. So this, now we can actually see the critical value predicted for the square of the energy predicted by the variation approximation is 6. K can be simply set equal to 1. 6, and the exact analytical solution is 5.33. So it means that actually there is some discrepancy between the variation approximation and the exact numerical result for the critical point, but it is not large. So it's actually here is written that in terms of the squared energy, the relative error of the variation approximation is about 10%, a little bit more than approximately 10%. Okay, now another ramification of this topic, this time we can look at this system. This system represents a rather popular topic, which is called parity time or PT symmetry. So when we looked at the previous model based on this system of coupled equations, because this system is completely conservative. It can be derived from its Hamiltonian. It also has its Lagrangian, and the Lagrangian in particular was used to develop the variation approximation. Now, the parity time symmetric system is, strictly speaking, a dissipative system, but a very special kind of the dissipative system when actually it includes symmetrically placed dissipation or loss and amplification or gain, so that they are placed symmetrically with respect to each other, and their strengths are exactly equal. So we have some amount of loss placed at one point, and some exactly the same amount of gain placed at the mirror image of that point. So such a dissipative system with a mutually balanced but separated, spatially separated gain and loss, they are called PT symmetric or parity time symmetric systems. For the first time, this concept was introduced, so to say, purely theoretically in quantum mechanics, where actually experimentally it was not realized, but later it was understood that it can be implemented in optics. In optics, in particular, in the case of the dual core fiber, it's rather easy to implement it because we can take again our dual core configuration, but now we can assume in addition to that, that one core carries gain. So the gain is represented here by the positive coefficient gamma. If we just look at this evolution term and compare to the gain term, and this is term contains u, this is also a tax upon u, we see that this term by itself, of course, will immediately give rise to the exponential growth of any perturbation with the growth rate gamma. Simultaneously, we assume that in the parallel core, we have the loss, the dissipative term with coefficient minus gamma. And they are still coupled linearly by the same pair of terms as we discussed before. Now here, a non-trivial problem is, first of all, actually we now only PT symmetric solitons can exist. In this case, it's quite obvious that unlike what we discussed a few minutes ago, we should not exist the existence of asymmetric solitons. For what reason? If we have different energies of solitons in the two components, it's obvious that then, for example, if we have larger energy in this active core where we have the action of the gain, the result of the rate of energy supply from the gain will be definitely larger than the rate of the energy loss in the parallel core. Therefore, the system will blow up essentially. It will start to pump energy into itself exponentially. Or on the other hand, if we have larger energy in the dissipative core, then the system will start to continuously lose its energy. For this reason, the asymmetric soliton cannot exist. Now, what is non-trivial here is to study the stability of the PT symmetric soliton, which has equal energies in the both components, but its stability is not obvious. Why it's not obvious? Because obviously the presence of the gain in one core actually is a drive for the instability. On the other hand, we have here the loss term, which can try to suppress the instability. So what may happen, qualitatively speaking, we may have some small perturbation. For example, the small perturbation will be amplified by the gain in this active core. However, this growing perturbation will simultaneously have a chance to tunnel through the linear coupling from the first core into the second core. In the second core, it will be suppressed. Essentially, it will be killed by the loss. And therefore, it's not obvious what will happen. If the presence of the gain, which drives the growth of the perturbation in the active core, will be enough to destabilize the system, or maybe this coupling and the possibility to suppress the growing perturbation by actually transferring them into the dissipative core and killing them there, maybe it will be sufficient to stabilize the system. So this non-trivial problem admits an exact analytical solution. I will not actually tell you in detail how it could be obtained, but just it was possible to solve it exactly analytically. Well, of course, the exact analytical solution was based on the analysis of the linearized equations for small perturbations. So what was done, first of all, the PT symmetric solitons can be easily found in the exact analytical form. Then what is non-trivial, one should derive a system of linearized equations for small perturbations. And then, fortunately, in this particular model, it's possible to provide an exact solution of those linearized equations, which a particular exact solution which account for the onset of the instability. And the final result is written here. The final result is written here, and the final result is that this PT symmetric solutions, solitons, remain stable as long as their squared energy is smaller than this particular critical value. So if gamma is equal to 0, we don't have new terms. It will be exactly the same criterion for the stability of symmetric solitons, which we discussed a couple of minutes ago in the dual core fiber. Now, if we introduce gamma, we see that now the critical energy above which the soliton becomes unstable becomes smaller, because this factor is smaller than 1. Still, we have, in spite of the presence of the gain and loss, we still have the stability region, provided that gamma is smaller than 1. But when gamma is smaller than 1, what it means, actually, physically speaking, if gamma is larger than 1, it means that eventually the gain and loss factors become stronger than the linear coupling. So as long as linear coupling is stronger, we still have some stability region. But when gamma becomes larger than 1, the coupling is no longer able to suppress the instability, and then the solitons become completely unstable. But the conclusion is that above this critical value, we have still the stability region for the PT symmetric solitons, which is quite a non-trivial result, and it was also verified by direct numerical simulations. And once again, let us stress that when the PT symmetry is broken, in particular when gamma is larger than 1, so that we are no longer able to support the PT symmetry of the solitons, this unstable PT symmetric solitons are not replaced by any asymmetric solitons. This is unlike what we discussed before, because in this case, when the PT symmetry is broken, the system actually blows up. Then we will observe the exponential growth of the instability. Okay, so this is the end of the particular discussion of the dual core optical fiber, and it also included the discussion of its parity time symmetric generalization. And now we will have a new particular topic, which still belongs to the general theme of the spontaneous symmetry breaking, and this will be the spot. Okay, let me just very briefly mention that what will we do? We will now consider this particular with a double well potential. So we see that this will be the two-dimensional system, as a matter of fact, with this quasi one-dimensional trapping potential, and we see the potential consists actually of two rectangular potential wells, which are separated by some distance, but the distance is finite, which means that the wave function will be able to tunnel across the barrier from one rectangular potential well to the other and in the opposite direction. So this, the last things to mention today, maybe just to show the equation which will describe this model. So this will be the two-dimensional nonlinear Schrodinger equation. Once again, the sign plus here implies its self-attraction, which can create solitons. But then quite a non-trivial problem will be the stability of two-dimensional solitons in this model. And U of X is exactly this double well potential, which is formally introduced here, but it's actually was introduced in the obvious form by means of this simple diagram. Okay, so really the last thing to mention is that what we will try to do, first of all, we will try to find stationary solutions in this obvious form. It's written in actually the notation is written as for the Bose-Einstein condensates. So mu may be called the chemical potential because the model, this two-dimensional model is relevant in principle for the Bose-Einstein condensates. And then we will have to try somehow to solve the stationary equation, and we will be interested in soliton solutions which are localized, and then we will try to see if spontaneous symmetry breaking we will be able to predict the spontaneous symmetry breaking for these two-dimensional solitons, and symmetry breaking should happen between the parts of the wave function which is trapped in these two potential wells. So, Emmanuel, I believe I must stop here.
Yes, it is 4:30 exactly.
Yes. Okay. So we will exactly from this point we will continue next Tuesday.
Next Tuesday, yeah. Okay, thank you
for
very
your
much.
interest. Okay,
Thank you very much.
I will stop sharing the screen. Yeah. I guess
After that, we invite Professor Alain to share his screen. Alain? Alain, can you open your microphone?
Yes, I think my mic is up.
Yeah, it is now open.
Okay, good. So thank you. Can I start?
Of course, yes.
Okay, thank you. So hi to everyone. Today we are going to continue with the chapter 3, who's dealing with the properties of acoustic polaron in nanostructure. It's a main chapter who contain many parts. As we know, last month we investigated the generality on acoustic polaron in nanostructure. As we already aware, is that beside the optical phonon, that have the high frequency, we have also the acoustic phonon, and that acoustic phonon interact with the electron and form what we can call the acoustic polaron. And as we know, when we reduce the dimension or when we are talking in terms of the low dimensional structure, there are several new phenomena on this material. And still in the chapter 1, when it was focused on the generality, we expose also the many kind of low dimensional structure. And we can mention there was 1D, 2D, 3D, and 0D dimensional structure. And those low dimensional structure was different in terms of the density of state. So we see, for example, that the density of state was having the continuum behavior to the ladder behavior and to the discrete behavior. And we conclude from there that the discrete behavior is of the density of state was the behavior resemble the atoms. That's why for the low dimensional structure who exhibit the discrete behavior was really taken in consideration. We are going to mention about the quantum dot and the quantum whirl, because the quantum dot, the behavior of the density of state was discrete, and the quantum whirl was the thing has the kind of the ladder behavior. So it means that this motivate the interest of a researcher to focus on the quantum whirl. So still in this chapter, introduction chapter, the generality, we already highlighted the impact of the quantum confinement in the properties of low dimensional structure. So this bring to take into consideration the confinement of all low dimensional structure. We already highlight the fact that the description of this polaron issue, either the acoustic polaron or the optical polaron, was described by the Froelich type Hamiltonian. And that Froelich type was imagine a polaron as a quasi-particle formed by two quantity as an electron and the phonon. That's why the Froelich model is formed by the Froelich Hamiltonian is formed by the kinetic energy of the electron, the part of the phonon, and the part of the interaction between the electron and the phonon. We will see that describing the acoustic polaron, we are going also to focus to use that Froelich Hamiltonian, but the particularity or the difference will be on the amplitude of the interaction between the electron and the space and the acoustic phonon. We will see that from there, the amplitude of the interaction between the electron and the acoustic phonon will be different for the one of the optical phonon. It is from there that we will see that the Froelich Hamiltonian or the Froelich polaron deal with a large polaron. So in this large polaron, the dimension of the polaron is more than the lattice parameter. And contrary to the acoustic polaron, the dimension of the polaron will be local. So the dimension will be less than the lattice dimension. That's why we call in terms of the deformation. And this deformation is local due to the fact that the radius of this polaron, acoustic polaron, is less than the lattice parameter. And in chapter 2, we have already also present the method or the material and the method, and especially we distinguish three main methods. The method for the low coupling, while we talk in terms of low coupling, what we should know is that we measure the coupling in terms of alpha. So this alpha is the strength of the coupling between the electron and the phonon. So when, for example, this strength is less than 1, we are dealing with the low coupling. And for the low coupling, the method appropriate for this low coupling is the Lilopine method. When also the alpha is between 1 and 7, we are dealing with the intermediate coupling. And when alpha is greater than 7, we are dealing with strong coupling. And for the strong coupling, the Pekar type variational method is appropriate for this kind of coupling. And the Ubrecht method is also appropriate for the intermediate coupling. But we should notice that for the all coupling method, Feynman established a Feynman integral to tackle either the weak coupling, the intermediate coupling, and the strong coupling. And also, Ubrecht modified the Lilopine method in such a way that we can also tackle the coupling, the problem, the polaron problem. Why not be afraid of the consideration of the nature of the coupling? So today we are going to use this element. We are going to use this element to study the bound magneto-acoustic polaron in asymmetric Gaussian confinement potential quantum world. So it means that we are going to consider an acoustic polaron under a magnetic field. And in this study, the magnetic field will be taken into account through the potential vector. This potential vector will bring the magnetic field in the problem. And also, we will see that to have something who can be resembled of what is existing in the nature. So we can say that the nature is not symmetric. It means that the dimension, the properties of the nature is not exactly the same according to the direction. So that's why to be near of the reality, we consider an asymmetric Gaussian confinement. And that asymmetric Gaussian confinement means that the confinement in certain direction is different for the confinement in the another direction. So especially, so the properties of a weakly coupled to longitudinal acoustic phonon in asymmetric Gaussian confinement potential world subjected to the magnetic field and the Coulombic impurity will be investigated in this lecture. So we already highlighted the effect of the impurity on the nanostructure. So the impurity we presented it last time highlight the properties. That's why investigating the low dimensional structure, we cannot forget about this impurity effect. So specifically, we are going to evaluate the ground state energy and the related binding energy of the acoustic polaron. So the binding energy will be calculated by taking separately the electron, the energy of the electron, the energy of the phonon, and the ground state energy. By doing the difference between these separative electron and phonon and the ground state energy, we can have the bounding energy. And from there, we'll see the effect of the magnetic field, the barrier height, and the range of the asymmetric Gaussian confinement potential quantum world on this parameter called the bounding energy. We can still investigate the strength of the coupling of the Coulombic, let us say the Coulombic interaction. We should know that here that we measure the Coulombic interaction in terms of a term of beta. This beta will characterize the strength of the Coulombic interaction. Also, we will see that there's a certain cutoff frequency, cutoff wave number. We will also see the impact of that cutoff wave frequency or cutoff wave number on the binding energy. And after, we are now going to investigate the property or the related relation of the cyclotron frequency in addition to control the quantum world. And this quantum world is not taken in consideration randomly. This quantum world, as a quantum dot, exhibit a good property compared to the ball material. So what we should know is that due to the advancement in the nanotechnology, the physical properties of low dimensional structure, and as I said before, as low dimensional structure, we can consider quantum world, quantum dot, quantum world, quantum wire, make people to be focused on it, and especially on quantum world, because they exhibit more properties, and those quantum world can see the application in telecommunication, in microelectronic devices, in solar cell, in quantum computer, especially in solar cell, because we realize that for the solar cell to absorb more energy, we need to use either a quantum dot or the quantum world material. And especially also for the quantum computer, because those nanostructure, those low dimensional structure exhibit the quantum nature. And for the quantum nature, with this quantum nature, you permit us to imagine a situation where we can have a superposition principle. And if we use this superposition principle to enable us to enhance the storage of the information. And so that's why more scientists devoted their research by looking for the physical properties of the low dimensional structure. We will see, for example, that some semiconductor used for small size quantum system as the arsenic gallium is one that have focused more attention because the coupling strength of this material is still weak, and with this weak coupling constant, will be enabled to tackle properly the properties of a semiconductor. Also, with this low dimensional structure, especially quantum dot and quantum world, the confinement potential playing a very important role in modulating the nature or the properties of quantum world will be also the main object of study this quantum world. And this quantum world with parabolic potential is an effective theoretical model that representing a real case, representing a real case because, as I said before, we cannot consider a system as a symmetry. So all systems normally may be, the properties of system may be different according to the dimension of the structure. That's why more intensive theoretical and practical work are focused on it. So we can see, for example, in the literature, that many people are focused on the confinement potential, like hyperbolic potential. For example, we can see also the cylindrical potential and the Gaussian potential. So, but we should realize that for all those potential, the potential with more variation parameter will exhibit the property, the real property of the structure. And by examining this, we see, for example, the role played by the magnetic field or the electric field, the noise field, the Coulomb field, the temperature, and all those other parameters on the properties of the low dimensional structure. So as we know, we have already investigated the electron phonon, the electron optical phonon interaction or role in the properties of quantum structure. So today is to focus on the electron acoustic phonon, the role of the electron acoustic phonon on the properties of low dimensional structure. So we can say that several authors, many authors examine that question, especially the acoustic deformation potential. As I say, the acoustic deformation potential is local. It's local. Why the optical polaron is not local, is on the lattice. So we have the collective excitation, why the deformation, the acoustic deformation potential is local. So it means that the deformation potential is a parameter which describing the local change of the electronic energy in the crystal induced by the acoustic phonon. So the idea here of the acoustic phonon first bring to the center by Toyozawa. As I say, that Toyozawa instead saying that the acoustic polaron is local compared to the optical polaron, who is taking the polaron in the long-range optical polarization. So, in this case, the acoustic polaron is a kind of the surf or the short-range deformation potential instead of being a long-range optical polarization. It is well known the different behavior of the acoustic polaron from quasi-free state to the self-trapped state is due to the electron-phonon acoustic phonon interaction. So we see, for example, that if we consider a situation where we are not taking in consideration the interaction between the acoustic phonon and the electron, we will see, for example, a big difference compared to the one who is free. So if, for example, electron is not interacting with the acoustic phonon, we will see, for example, that this behavior will be very different to the other behavior. That's why many scientists are focused on this to investigate this the new property bring by the interaction between the electron and the acoustic phonon. And we, first of all, calculate the ground state energy Tokuda, for example, acoustic polaron in one-dimensional using a Lagrange multiplier addition to the sham of the variational approach based on unitary transformation. What we should know is that as we are going to see, for example, in this lecture, we are going to use the unitary transformation, especially two unitary transformation. The first unitary transformation will be the end. After the second unitary transformation, we are going to use as a shift operator. This unitary transformation will be as a function of the variation function f q and f star q. This shift operator will permit us to, after using those two unitary transformation, to have that the electron may move freely without interacting with the acoustic phonon, and there's some condition where the electron can move not freely but with the cloud of the acoustic polaron, where Peter and G use the Feynman part diagram method to investigate the polaron, the acoustic polaron. They have also the ground state and discuss for the different approximation, the reason of the transformation, or the nearly free or the self-trapped electron state. So they see, for example, the situation where we assist of the self-trapped electron, and that self-trapped electron was due to the acoustic around acoustic polarity. And this free is because slap with the potential this as the Feynman method. So they use the vibrational variational method to calculate also the ground state energy and the derivative of the acoustic polaron. So it means that when we consider the electron interacting with the acoustic polaron, the ground state energy is deviated from the one for the free electron. So that's why it's also necessary to investigate the self-trapping transition for acoustic polaron in the slab. So the impact of the magnetic field and the behavior of the polaron in quantum world make the subject of the polaron more interesting, because in the presence of this magnetic, field is equivalent to adding another confinement. We have already presented or proved that adding a magnetic field in the system is equivalent to enhance the confinement. So as we know, we highlighted the effect of the confinement. It means that adding the magnetic field in the study will highlight the study and also make in such a way that the study will resemble for the reality, because a system cannot work without be exposed to some field, and for example of the magnetic field. Still in the literature, Gardin studied the dispersion of the magneto-acoustic polaron using the green function techniques. So he see, for example, how the green function techniques can be used to study this dispersion of the acoustic polaron subjected to the magnetic field, and why show a Fujita use the Fujita diagram method and the Kubo formula to examine the magnetic field correlation of cyclotron resonance line with the electron longitudinal acoustic phonon interaction. He found that the cyclotron resonance line width for all acoustic polaron live with increased field density, and in the same direction, SAB apply adiabatic sham to acoustic polaron to form bond with the impurity to see, for example, the effect of the magnetic field. The adiabatic sham here is due to the coupling, to the strong coupling between the electron and the acoustic phonon, and from there he exhibits the enhancement of the ground state energy due to the electron acoustic phonon interaction will become more important with increase the magnetic field intensity. And this is obvious because, as I said before, the magnetic field is equivalent to the confinement. As we know, as we confine particles, we enhance their interaction, the interaction between those quasi-particles. And still in the literature, Xingzhu investigate the effect of the magnetic field on the variational frequency, the ground state energy, and the ground state bounding energy for the weak coupling polar optical polaron in asymmetric gallium asymmetrical Gaussian confinement potential quantum world using the Ubrecht-like variational method. And from here, he see, for example, that for the polar optical polaron, the system, the system was crucially modified by the parameter of the coupling between the electron and the optical phonon, and also the influence of the magnetic field and the barrier height of the weak coupling bond acoustic polaron was also putting in hands. So as I said before, in this paper, or in this lecture, we will highlight the effect of the parameters such as the magnetic field, the Debye cutoff wave number, the strength of the Coulombic impurity, and the height of the range of the asymmetric Gaussian confinement potential were on the properties of this quantum world. And this is to highlight how we can use all those parameters for the controlling of the quantum world property. And let us move to the theoretical and the model to say that here we consider an electron moving in the crystal and confined in the asymmetric Gaussian confinement potential quantum world. This asymmetric Gaussian confinement potential quantum world will be given by these terms V of Z. And we will see that this electron moving in this kind of crystal and confined with this asymmetric Gaussian confinement potential world will interact with this phonon. This phonon is the acoustic phonon. This interaction will be happen via the deformation potential. We will see, for example, that the amplitude, as I said before, of the interaction between the electron and the acoustic polaron is different from the amplitude of the interaction between the electron and the polaron of the optical phonon with this amplitude. This amplitude is proportional to the square root of Q. And we'll see here that the magnetic field will be parallel to the direction of Z. And this parallelism will be expressed, or the magnetic field will be bring here by the vector potential A. We see that this vector potential A is equal to B on 2, represented in the minus Y and X and 0 in the Z component. So it means that the general Hamiltonian will be given by this term. Let us say that this first term is the electron momentum energy. So this is the kinetic energy of the electron. As I said before, this second term is the confinement. This is the confinement of the asymmetric Gaussian confinement potential quantum world. And we are going to see how this confinement is considered as the asymmetric, but we can still say that it's considered as an asymmetric Gaussian confinement potential quantum world because firstly, the properties is differ with the direction. As I said, the third term, this third term with minus beta on R represent the impurity, and that impurity is bringing by the Coulombic terms. This is the Coulombic terms who is given by minus beta on R. So investigating the role of this impurity will be easily, we are going to use this parameter beta to examine the strength of the impurity according to the property of our system. And these terms, these four terms here stand as the energy of the acoustic phonon. This energy of the acoustic phonon is proportional to h bar omega q. This omega q is this dispersion will be linear to the wave vector q. We will see it in jitter. Why? The last term here represents the interaction between the electron and the longitudinal acoustic phonon interaction. We'll see from here that this A in this part, the first part on the kinetic energy, is the vector potential. Why? This M is the electron band mass, and E is the electron charge density. As I said before, the frequency, this phonon frequency, is expressed to the linear dispersion relation with the acoustic wave number or wave vector Q. So this W Q is equal to SQ. This S is the sound velocity. This is the sound velocity. And we can also say that this expression of the Hamiltonian of the system is expressed in terms of AQ and AQ minus Q. This AQ is the creation, this AQ minus Q plus, this A plus is the creation phonon, is the creation acoustic phonon, while this AQ is the annihilation acoustic phonon. So we will see that this P and R is the momentum, this P is the momentum of the electron, and this R related to the position of the electron. As I say before, is that there's among the two unity transformation that we are going to use here, one will help to eliminate this position coordinate, and the other will help to eliminate, to create a dispersion or a displacement on those operator A plus and AQ. So we have, for example, the relation between this dimensionless electron longitudinal acoustic phonon coupling strength alpha. This relation is linked. Alpha is linked to the deformation potential. This relation is given by this this relation 2, where we see, for example, a link between the deformation or the dimensionless electron longitudinal acoustic phonon coupling strength alpha and the deformation potential. This deformation potential here is given by dRc square. And we see, for example, this is a local deformation potential. And in this relation, rho stands as the density of the crystal. And we see, for example, that the confinement potential, so this asymmetric Gaussian confinement potential quantum world is given by this term. And we can see from here that the nature of the potential is different when Z is greater than 0 and different when Z is less than 0. We say here for the one-dimensional structure, because here the confinement is in Z direction, we see that this V is V of Z. We see from here that the potential is asymmetric. Asymmetric because the value or the properties depend to the direction. This is the positive direction of Z, this is the negative direction of Z. And for those two directions, we have two behavior. We should also see in this potential, in this confinement potential, that this V0 stands as a high of the asymmetric Gaussian confinement potential quantum world, where this L is the range of the confinement potential world. We see, for example, of what Boris was presented, his range, the range of the confinement was A. The last diagram that Boris showed, the range of potential, his range was A. So we see that this is the range of this asymmetric Gaussian potential confinement quantum world. This is the range here, L. So as I said before, the impurity, this impurity is measured by his strength. This strength of the impurity is given by this beta. So we have the strength of the impurity, we can be measured by beta and can be also expressed in terms of the high frequency dielectric constant epsilon infinity. This expression is given by this beta is equal to E square epsilon 0 h bar c. And we see from here that this beta is proportional to E square epsilon and epsilon infinity. And from here, we can see that this expression is exactly the expression of Coulomb, because this E square have the dimension of two interacting charges. If now we apply the George approximation on this Hamiltonian, we arrive at a situation where the Hamiltonian will transform to this, where the first term is the kinetic energy P square on 2m. We see, for example, that this second term will bring the magnetic field through the cyclotron frequency WC, and the confinement, who is x square and y square, is given by this third term. And this third term is given by m omega c Lz on 2. And the potential V of Z will remain there, and the impurity minus beta on R, and the phonon path and the interaction between the electron and the acoustic phonon path, who is given here as the last term. If you use a unit where we can set h bar equal to 0, m equal to 0, and the sound speech equal to 0, and apply the modified Lilopine transformation on this three-dimensional system, as I said before, the first Lilopine transformation, who is given by this unitary transformation U1, who is given by exponential minus I sum on Q R A Q A plus. The aim of this first unitary transformation is to eliminate the position, the electron position R on the Hamiltonian. And this second Lilopine transformation, unitary transformation U2, who is a function of those variational function FQ and FQ star, will take as a shift operator. So will permit us to shift all the operator in the equation 5. So by using this this U1 on all terms of the equation 5, and the results we use also U2, this unity transformation is using in this form. So we use, for example, for this H, for example, we apply on the left U1 minus 1, and at the right U1. And the results, the obtained results, we apply also U2 minus 1, and on the right U2. This means that we apply the first and the second unity transformation. And after applying this first and the second unitary transformation to this Hamiltonian, we need now to obtain the ground state energy. This ground state energy is obtaining by mean with the ground state wave function. This ground state wave function, if we mean by the ground state wave function, we are going to apply at the left this ground state wave function is taken as 0 at the ket 0 and phi 0. This phi 0 represents the electronic path of the wave function, and this 0 represents the phonon vacuum state. So it means that to have the ground state energy, we are going to apply this transform Hamiltonian H prime to this wave function, ground state wave function phi, with phi 0, which is equal to 0, this ket 0 and phi 0. Why? Taking in consideration that the vacuum fulfill to certain properties, and among those properties, we can say that A, when we act the vacuum, the phonon, the 0 phonon state on the annihilation operator, we have 0, and the square of the ground state wave function is also equal to the square of this 0 phonon state, 0, which is equal to 1. And why taking in consideration also that this relation, this sum of Q, this variational function f Q square is equal to 0. If we take this in consideration and also apply the conservation of the total momentum, this conservation say that we have this wave function, we apply the first and the second transformation on the total momentum, this will give 0. We should see, for example, that this total momentum is expressed as the momentum of the electron and the momentum of the phonon, of the acoustic phonon. So these two, where is those two transformation? Yeah, these two unity transformation, yes, U1 and U2, if we apply it to the total momentum, we are going to obtain 0. It means that this is the conservation of the total momentum. This conservation is also after applying U1 minus 1 and U2 minus 2 and U1, U2 on this total momentum, we are going to mean by the mean value, the ground state energy, and obtain 0. This ground state, this electron ground state wave function is, or electronic path will be given, you know, the phonon path is given by this 0 phonon state ket 0. This ground state, this electronic path of the ground state wave function is given by this. And we see, for example, that in this expression, we have the variational parameter, lambda, and this variational parameter will be helpful to mean the value of the obtained energy. So it means that if we apply the first and the second unity transformation, if we apply the first and the second unity transformation, and also applying the wave, the ground state energy composed by the 0 phonon state and the electronic path of the ground state energy wave function, we arrive in this expression, equation 14. We see that in this expression, we still having the first kinetic energy, and we'll see that from this first path, we eliminate the value of m. because M, this Hamiltonian or this energy is taken into consideration where M is equal to H bar, who is equal to 2,1. This is the unit, our unit here. H bar is equal to M, who is equal to the sun speed, who is equal to 1. That's why we cannot more see the M in this expression. Also, we see from here that the impact of the potential on A1, on U1 and U2 is not taken in consideration. So U1 and U2 are not affecting this P square and did not affect also V of Z. The same observation is seen to the impurity term. This impurity term is here represented by beta on R. We can also see that we see terms, we take terms after terms. These terms, after this, let us move to this. These terms, we apply U1 and U2. U1 and U2 did not affect considerably, change the expression, this second expression. We see that after applying U1 and U2 with first and second unity transformation, we remain have x squared plus y squared with this electronic path of the electron, the electron wave function. We still have this 12th path with the path with LZ. This LZ, this is the one. We have this path of the LZ, and we see that this path of LZ is still there, and the one of the phonon, we see that the path of the phonon energy is drastically changed, and we see that this is the path of the phonon energy, and the path also of the interaction is given by this term. We see from here that if we ignore this first term, this transformation did not contain more the electron coordinate, and as this ground state, this variational ground state energy is a function of the variational function f q and f star q. To have the expression, it is necessary to derive this equation with respect to fq, and also derive this equation with respect fq star. If we derive this equation with respect as a variational energy, we derive this equation with respect to fq and take the answer equal to 0, we can subtract the value of fq. Or derive this equation with respect to f star and put the answer equal to 0, we can obtain fq. And we replace in this expression fq and f star by the expression and obtain the ground state energy. Also, instead of having the value of the ground state energy, let us change this discrete sum. The discrete sum is appearing in this expression and in this expression by the integral form. This discrete form is changing by the integral form by consider V on 4 pi cube, the volumic integral of GQ. And as we integrate with respect GQ, we should remember that the upper limit of this integral will be the cutoff wave number Q0. And from here, we obtain this expression. We see that this expression E0 is given by 3 on 4 lambda square omega c square on H lambda square minus V0 1 plus 1 on 2 lambda square L square root minus 2 beta lambda on square root of pi minus alpha on pi Q0 square minus 4 pi plus 8 ln 1 plus 1 on 2 Q0. So from here, we can see that this variational energy E0 is still a function of the variational parameter lambda 0. This variational energy is still a function of the magnetic field, as the magnetic field is related to the coupling to the cyclotron frequency. This variational energy is also a function of the height of the asymmetric Gaussian confinement potential quantum wire V0. This variational energy is also a function of the range, the potential range L, and also function of the cutoff wave number Q0. Let us now derive this expression to eliminate the variational parameter lambda. If we try to eliminate the variational parameter lambda, we are going to derive this and obtain this equation in terms of lambda 4 minus V0 on 2 L square, this 1 plus 1 on 2 lambda square L square on minus 3 on 2 minus 4 beta on 3 square root pi lambda cube minus omega c square on 6 equal to 0. So it means that we are going to solve this equation, and for each value lambda, we will replace in the ground state energy to obtain the ground state energy correspond to each value of the lambda. As now we are looking for the bonding energy, express the bonding energy will be taken, we will consider that the electron is not coupling to the acoustic phonon. In that regard, we will use the literature to recall the value of the electron or the free electron energy E, and to use also the value of the phonon, the acoustic phonon free phonon energy EPH, each phonon. If now we consider that, because to obtain this was considered that the electron was coupling to the electron phonon coupling constant. And now, if we consider that the electron is moving freely and the phonon is coming with his own energy without any interaction, if phonon, from here, we can really see the ground state bonding energy EB. What is the ground state bonding energy for the electron and the acoustic phonon? This ground state bonding energy will be expressed by this formula. This EB will be the energy of the free electron, EE, plus the energy of the free phonon minus the energy of the ground state, minus the ground state energy. And finally, if you replace this E0, this EE and E phonon and E0 by this term, we finally obtain this expression as the bonding energy. This expression stands as 4 alpha on pi on Q0 square minus 4 Q0 plus 8 ln 1 plus 1 on Q0 minus this omega c square, this cyclotron frequency square on this H lambda square plus V0 plus 1 on 2 lambda square L square on minus 1 on 2 plus beta 2 beta lambda on square root of pi. So we see that this binding energy is a function of the coupling constant between the electron and the acoustic phonon. It means that as analytically we have this expression, from here we can see that as the coupling between the electron and the acoustic phonon will be high, the binding energy will be high also. The binding energy is proportional to the coupling constant between the electron and the acoustic phonon. We can also see from here that the binding energy is a function of the impurity. As there are more impurity in the crystal, as more the binding energy will be increased. And we can also from here seeing that as in the crystal with more impurity, we are supposed to have more phonon, either the acoustic phonon or the optical phonon. As we are dealing here with the acoustic phonon, we see that with the impurity in the medium or in the system, this impurity highlight the effect of highlight the number of the phonon, and from there enhance the binding energy between the quasi-particle and the acoustic phonon. Also from here, we see how the high of the confinement potential V0 can be helpful can modify the binding energy. And let us now try to see some numerical results, and on those numerical results we'll specifically see the impact of the cyclotron frequency, which is represented here by WC, the impact of the high V0 of the asymmetric Gaussian confinement potential quantum world, and the impact of the cutoff wave number Q0, also the impact of beta, who is here, the impurity, and also the impact of the range of the asymmetric coupling, the asymmetric Gaussian potential confinement quantum world R on the properties of the system. So let us start by evaluating this ground state energy E0, this ground state energy E0. We see, for example, that here, this is the increased value of the potential high. And here we have, for example, the increased value of the cyclotron frequency. We talk in terms of the cyclotron frequency here, is talking in terms of the magnetic field. And this graph is plotted for the coupling, for the law, for the weak coupling regime. This weak coupling regime is characterized by the strength alpha equal to 0.01. Is also plotted for the impurity the strength of the impurity characterized by beta equal to 1.5, and it is also plotted for the cutoff wave number Q0 equal to 15. And from here, we see that the absolute ground state energy E0 increase with the potential high E0. As the potential high is increased, the absolute value is also increased. We can see it with the increasing of the potential high. We have also the increase of the absolute ground state energy E0. This, we can also see from here that as the confinement, the cyclotron frequency, WC, increase, we still have the reducing of the absolute value of the ground state energy. This can be seen even from this, this observation. We can see that this has a negative value, while this has a positive value. It means that the effect of the cyclotron frequency will be the contrary of the effect of the high of the high of the high of the high of the asymmetric Gaussian potential confinement quantum wave. That's why, as this is decreasing with the increasing of the cyclotron frequency, this one is increased with the absolute value of the cyclotron frequency. Let us also see what is happening on the binding energy for the same parameter. The same parameter means what? We have the law, the weak coupling regime, who is expressed here by the coupling constant alpha equal to 0.01. The impurity strength beta equal to 1.5. The cutoff wave number Q0 equal to 15, and the range equal to 20. We still have the increasing function of the binding energy as a function of the height of the potential V0. We see as we are increasing the height of the potential, the binding energy here is increasing. And also, we still have the reduction of the binding energy as the coupling, as the cyclotron frequency WC is increased. We can also see it from the expression that this binding energy is expressed in terms of the high V0 and WC with minus, so the sign here is different. That's why we will exhibit a different behavior compare each other. As this exhibit this behavior, as I said before, it means this high of the cyclotron of the potential, the asymmetric Gaussian potential, can be used to modulate the value of the binding energy, and be modulate also to modulate the value of the ground state energy. The same observation is also related to the cyclotron frequency. So the cyclotron frequency can be useful to modulate the binding energy and also the ground state energy. And we can also see that as an absolute value of the ground state energy and the ground state bounding energy are enhanced with the increasing of the barrier high, this barrier high can be very useful in the properties of quantum world. And this behavior is justified by the fact that the Gaussian confinement potential in the groove direction of the quantum world is similar to incorporating another confinement on the electron. We see, for example, that as we increase the confinement in the structure, the confinement obliges the electron to be coupled to the phonon. As this coupling arises, we arrive at the increasing of the properties, either the ground state energy or the binding energy of the electron and the acoustic phonon. And this produces the larger electronic density. And with this larger electronic density, we increase the interaction between the electron and the phonon. So, as this confinement increase, the number of phonon increase in the system, increase the interaction between the electron and the phonon, and also increase the properties. We may see it from here, this ground state energy, that the ground state energy is increased with the increase of the potential, and we can also see it for this binding energy. And we can see that this effect is observed for the ground state energy and for the ground state energy. It means as this binding, as this potential increase, as stronger the confinement of the electron in the groove direction arise. And consequently, we have more electron, more phonon, firstly, who are going to interact with more phonon. And we can see that there is an increasing with the high of the asymmetric Gaussian confinement potential world. Let us also conclude about the cyclotron frequency. We see from here that as the cyclotron frequency was enhanced, the same observation was also seen here. As the cyclotron frequency was enhanced, you have the decreasing of either the ground state energy and the bounding energy. If we analyze, for example, this term, on the binding energy, and this term in the cyclotron, in the ground state energy, we'll see that this term is responsible to the fact that the ground state energy and the bounding energy is decreased with the cyclotron frequency. So the cyclotron frequency has a negative value, will responsible to the variation of the ground state bounding energy. And for this reason, the ground state energy rise with the reduction of the cyclotron frequency. We'll see that if we reduce the cyclotron frequency, the bounding energy will increase. And we can also use this cyclotron frequency, as we said, for the barrier height of the potential in order to control the properties of the asymmetric Gaussian confinement, the asymmetric Gaussian confinement potential quantum world. Let us continue by analyze the effect of the impurity on the absolute value, ground state value is 0. We have already highlighted that the impurity in the system cannot be neglected. This highlighted was done by Givries, while taking in consideration many value of this impurity, and compare with the last value of the energy. He observed that as the impurity was increasing in the structure, the energy was also increased. What is happening after this lecture? Let us see in this direction. We are increasing the impurity. As we increase the impurity, the absolute ground state energy is also increased. As we reduce the impurity, the ground state, the absolute ground state energy is reducing. As I said before, by increasing the impurity, increase the number of the phonon. And we know the phonon is responsible of the resistivity in the material. As phonon are more in the structure, as more electron can interact with this phonon. And the resultant of this interaction will be the increasement or the enhancement of the properties of the structure. And this enhancement of the property is easily seen in this structure. We see from here that these properties, if 0, is increased with the increasement of the impurity, and this increasement of impurity is also the increasement of the number of phonon. Let us also see what is happening with the cutoff frequency, especially for the absolute value of the ground state energy. What is happening here is that this is the behavior of the absolute value of the ground state energy is 0 with respect to the cutoff wave number Q0. As the cutoff wave number Q0 is increasing, we arrive also at the increasement or the enhancement of the properties, and especially the absolute ground state energy E0. So this is the constant, this is the value who can be helpful to turn the value of the ground state energy. And another important parameter here is that for the low value of the cutoff wave number Q0, we have a small value, a small increasing behavior of the ground state energy. And from a certain value of the cutoff wave number, we have a kind of a parabolic, a kind of the parabolic exponential behavior of the E0 as a function of Q0. Now, if we need to study the cumulative effect of the impurity and the cutoff wave number Q0, we can easily say that the Q0 dominate on the impurity. This increasement is slowly. Why? For the Q0, as the Q0 is increased, the cyclotron or the parameter E0 can even reach the higher value. And this higher value is modulated by this Q0. We see, for example, that as Q0 is near of 0, and beta, the maximum, the impurity in the maximum in the system, the absolute value of the energy is around 7. If this maximum energy, if this impurity is still taking the maximum value, but with the maximum value of the cutoff wave number, we will see that the energy, the ground state energy, is red. This red means we have the maximum value. And we should notice here that this figure was plotted for the law or for the weak coupling alpha equal to 0.01. And this was also plotted for this V0 equal to 9. So it means that it was in this region of V0. And in this region of V0, if we see, for example, that the cyclotron frequency with the cyclotron frequency in this region, this ground state energy was around 9 or 10. But contrary, in this, we reach maximum value of the ground state energy. Still, this absolute value of the energy was plotted for the range L equal to 20, and the cyclotron frequency equal to 7. let us also see the behavior of the bounding energy. This bounding energy as a function of the impurity parameter and as a function of the cutoff wave number Q0. We still see that the impurity, which is represented here by the strength of impurity beta, increase the number of the bounding energy. This is caused by the fact that as the impurity in the structure exists, more phonons are exist in the system. As the number of phonons is increasing, the correlation or the interaction between this phonon and the quasi-particle will also enhance. This is numerically seen by the fact that the phonon, the bounding energy here, is leaving, even gradually, smoothly, from the lower value for zero impurity to the higher value with maximum impurity. This explains the behavior of this bounding energy. Let us look also the behavior of the bounding energy related to the cutoff wave number Q0. As we see in the graph before, we see that this bounding energy is still the increasing function of the cutoff wave number Q0. This increasing function of the cutoff wave number is smooth at the low value of the cutoff wave number and exponentially from a certain value of the cutoff wave number 20. We see from here, we are seeing an exponential parabolic behavior of the bounding energy. This exponential parabolic behavior of the bounding energy was also observed for the ground state energy. From here, we also see that this exhibits the cumulative effect of the impurity and the cutoff wave number Q0 on the bounding energy. It means those two parameters are the tunable parameter to manipulate the bounding energy. And if we compare, for example, the behavior of the bounding energy and the behavior of the ground state energy, we may see that the behavior of the bounding energy is similar to the behavior of the bounding energy. As the bounding energy is obtained by taking in consideration the energy of the electron in the free lattice plus the energy of the phonon in the free lattice minus the energy of the ground state energy. It means that it's the ground state energy who is dictate the behavior of the binding energy. That's why normally, as we are dealing, for example, with the ground state and the first excited state and the other excited state, as we have the ground state energy, this ground state energy indicate about the behavior, the general behavior of the structure. And that's why the bonding energy exhibit the same relation or the same behavior as the ground state energy. The only difference here is in terms of the value. The term of the value. We'll see that this is the high here is a bit greater compared to the high of the absolute value. So I think it's better to stop on this relational curve of the ground state energy as a function of the impurity and the cutoff wave number for today. So Emma, thank you, dear all. For
thank you. Okay, thank you, Alain. It's exactly 6 p.m.
Okay.
So the next lecture is planned for scheduled for next Tuesday. That will be 1 week exactly. At the same time, that is at 4:30 Beijing time.
Thank you.
Okay, thank you very much to everyone.
Thank you.
And bye-bye.
Bye-bye for everyone.
Thank you.
Okay.